Here we're going to cover 2002's question B3. This focuses on the Maclaurin expansion. Now, the formula for the Maclaurin expansion comes as part of the formula list that you get within the exam. But essentially, what it is you look at the value of the function and its derivatives when x is equal to 0 and generate a sequence from that. Now, the question gives us the function f of x equals ln cos x between 0 and pi over 2 for x. And we want to find the expansion as far as the term to the x to the power of 4. Now, in order to do this, because I know it's the fourth term, what I need is the fourth derivative. So I need f of x, I need to figure out f dashed x, f double dashed x, the third derivative of x, and then the fourth derivative of the function as well. I evaluate each of these at the value when x is equal to 0, and these give me the coefficients of each of my terms that I'm going to use within the equation. Now I know what f of x is. We're told that in the question. F of x is equal to ln of cos x. What I can do is take the derivative of that and figure out f dashed x. If I do that, take the derivative, I get 1 over cos x times minus sin x. That gives me minus tan x. And I then continue on taking the derivatives from then on. I know derivative of tan x is sec squared, so second derivative is going to be minus sec squared x. If I then take the derivative of minus sec squared x, what I end up getting for that one is minus 2 sec squared x tan x. And then the final one, the fourth derivative, much more fun because for this one we've got to use the product rule and the chain rule combined within one big function. What I end up getting for that one is I get negative 4 sec squared x tan squared x minus 2 sec to the power of 4x. So they all end up giving me what looks like relatively fun looking trigonometric functions. Now for each of these, what I have to do is evaluate their value at 0, so when x is equal to 0. So I want f is 0, f dash to 0, f double dash 0, the third derivative at 0, and then the fourth derivative at the value where x is equal to 0. Now, if I look at all of these, ln cos x, so x is 0, cos of 0 is 1, so I then look for ln of 1. We know that ln of 1 is equal to 0. I then want to look at f dashed x. Well, I know f dashed x is negative tan x. I want f dash to 0. Well, I know derivative of ln cos x, which is tan x, at 0 is going to be tan of 0, tan of 0, again gives me a 0. I then want to look at the second derivative, which is negative sec squared x. Well, I know sec x is 1 over cos x, and I know cos of 0 is 1. So what I'm going to end up with is negative 1 over 1 squared, which will give me negative 1. Now this one here, negative 2 sec squared x tan x. Well, again, I know tan x is 0 when x is 0, so this whole term here is going to disappear, and I'm going to end up with a 0. I've then got the fourth derivative again at the value of x is 0. This part here, because it's multiplying by a tan squared, that's going to equal 0. I've then got minus 2 times sec to the power of 4. Well, I know sec is 1 over cos. 1 over cos of 0 is just 1. So that's negative 2 times 1 to the power of 4, which is negative 2 times 1, which gives me negative 2. So what I do now is I plug all this together to get my Maclaurin expansion, and I can say, therefore, ln of cos x is equal to, well, 0 plus 0x. We don't need to worry about that. We've then got minus 1 x squared over 2 factorial. There's going to be no x cubed term. Then minus 2 times x to the power of 4 over 4 factorial. I can then simplify each of these and see what I get. So I end up getting for the first term is minus x squared over 2. The second one here, 4 factorial 2 divided by 4 factorial, gives me 1 over 12. So I then get minus x to the power of 4 over 12. So there you go. That's my Maclaurin expansion as far as the term in x to the 4. Now remember, it may want a term up to having the power of x to the 4, but that doesn't necessarily mean that every single term is going to be there in the final solution. Some of them may have a coefficient of 0, and if that's the case, we can ignore that term in our final answer and write down the solution up to that point.